All right, let's start. Hello, everyone. This is Dr. Yuzo. This is ECE 318, Electronic Circuit 1. And this is our 10th lecture today. And can you guys hear me? And also being able to see my shared screen in second. Here we go. Okay, should be able to see it now. All right, thank you, Kevin. All right, let's go on then. Today's lecture is actually nothing new to be taught. Okay, just trying to help you guys be ready for the upcoming midterm one. I think here's the review. Okay, I gave last lecture, and first of all, we have multiple choice problem. Total points is 15, and you either have 10 questions or 15 questions. So the point for each question might be different, okay, based on how many you have. Okay, and the three basically handwritten works. They're nothing but circuit analysis. Okay. One circuit for diode circuit, and in the diode circuit you have a AC source and the DC source, and therefore you're going to conduct a DC and AC analysis respectively. Which one must go first? Anyone remember?
DC.
The DC, right? Why is that?
Because you'll need the value of the current for the second part.
Wait, yeah, right. Basically, right. So we need what? The ID for the AC small signal model for the diode. Okay. So this is the question 2. Okay. And from the magnitude, you can also tell the AC source magnitude is going to be very small, way smaller than the DC magnitude. Okay, that makes sense. One is DC, another is small signal model. Okay. Do two things. Okay. And then you have a diode circuit. In this diode circuit, it's AC large signal, which means you only have an AC source, but the magnitude is large. Okay. Large enough for you to apply the large signal model of the diode, which is same as that for DC, right? DC model, same. And here, I'm talking about either half-wave rectifier or a full-wave rectifier, okay? And I'm planning to give just a half-wave rectifier circuit. Okay. Probably not exactly same as what we learned from lecture, but still, the procedure idea remains same, okay? Won't be exactly same circuit. And the last problem is the Clipper circuit. This is the thing we learned from previous lecture. We went through a couple of examples. Okay. And there's a standard procedure for you to go for to find 3 things. Remember 3 things. What are those 3 things? Anyone can remember. What are those 3 things for the Clipper? What are you looking for?
You need the range of the input AC source.
And?
You need to like sort of draw the circuit when the diode is on and off.
Okay, and?
Find specified VO or V naught.
Good. Okay, right. So this the logic, or say the procedure, very clear to Shane, and hopefully the rest of you guys as well. Okay, and this is the Clipper circuit. Okay. Basically, this is the review. What's going to be covered? Nothing should be surprising you. Okay, nothing should be surprising you, and to further avoid any messing up, I bring up this summary, which I gave in the past lecture ever. Okay. We are basically 3 models, right, for the diode, right? 3 models. One is the DC model. DC model of the diode is just like this, is a cut-in voltage V gamma, whatever the value is given, right? Just to be careful the orientation, right? This DC model for DC analysis. Second, we learn a so-called AC small signal model for the diode. It's just a resistor. Resistance value is equal to Vt divided by the DC diode current. So you can imagine if in the circuit you don't have a large signal DC, your AC small signal circuit won't do anything. Okay, and it has to have a big DC there to make the small signal AC works. Okay, so this is small signal model. Once again, the small signal means your AC magnitude is way smaller than the DC magnitude. Okay. The last one is AC large signal. This is what? This is our diode circuits, like rectifier, clipper. Okay, in where the AC magnitude is large enough and only AC in the circuit. Partner, could you please mute? All right, thanks. Okay. And so this is the 3 different models, and we are using them differently in different circuits, obviously, right? So as long as these are clear, then you shouldn't be messing up. By messing up, because in the past it happens like this. In the problem 2 here, the DC and AC small signal circuit, students using the diode and clipper circuit analysis procedure to do. Of course, you're gonna end up with like a messed up answer. And conducting DC analysis or even AC small signal circuit analysis in these 2 problems, absolutely messing up, right? That's what I mean by messed up. That kind of result or say answer are called a disaster. Okay, that you can imagine what the grade gonna be, okay? Because you're not even close. You're not even close. So the bottom line is to avoid that kind of a disaster from happening, right? All right. So with all of those being said, any questions? Any questions, actually? If no questions, obviously we gonna first of all we can talk about something here. Second here. This is the test run exam. Well, we got 3 more responses, which is good. And according to this questions, well, most of students remaining hating the online teaching and learning. And also to this one, accessibility of the multisym. I'm seeing one student saying, I haven't yet even think about it. Well, you really should. Okay, you really should. Okay, and I think you have. Okay? So the multisym, regarding the multisym, we had a announcement. A little bit updates about the multisym. Has everybody saw this? Everybody seen this?
Yep, I didn't look too thoroughly into it, but I did see the announcement.
Well, this is just a forum. A forum is the official forum from the NI, so it's more convincible. You know what I mean? It's not kind of electronics forum where some information cannot be guaranteed accurate. But this one is just telling you that it's normal for you to begin with 7 days, and then if you click the extension, it's gonna automatically increase to 45 days. Okay, this is the answer provided by NI employee, obviously. Okay, this is so-called update. Okay, so keep this in mind so that you won't do this extension thing until approaching to the Thanksgiving, right? For our final project. Any questions? Any questions for the exam? Any trouble of using lockdown browser and webcam? Any troubles over there? I'm not checking the uploaded file yet, but any trouble of doing those? All right, sounds good. So no trouble of uploading files either, right? I don't know. In my other classes, there were a couple of students uploading very big file, the PDF file exceeding even 20 mega. I don't know. It's very the quality of the picture and the file. It's very clear. Obviously, quality very high quality, very high resolution. However, is a little bit unnecessary. I mean, you sacrifice the file size too much. And the problem I had in reading those kind of high quality PDF is when I type something here, it takes me 2 seconds to be able to see it. 2 seconds is a lot, actually, when you typing the word, if you have some related experience. Okay. So somehow try to control the size of your file. Okay, don't make it too large. Exceeding 20 mega, is overwhelming. Okay, it's a little bit too big, abnormal, I would say. This is the thing. If no trouble, then I think you guys ready. By the way, when is the exam? What time is it? Yep, just one. Okay, just 1 p.m. It's 1 p.m. to 2:30, and then you have another 15 minutes to upload the file. But be very careful. Okay, the time shouldn't be an issue. You should have plenty of time. However, in case your timing is a little bit tight, be careful. Okay, the system is a computer system. With no mercy and with no mercy. Okay. When the time click on 2:30 exactly, the system shut off. You will not be able to upload anything. Remember this. Remember this. And Daniel is asking, you said Canvas grades are not accurate, right? What do you mean by grades are not accurate? Because the number shown there, say you have a midterm 1, and then let me see if I can show something.
Right. So what I'm saying is for that little 3-question quiz, like it's giving me a 0 out of 3, even though I took it. Yeah, like the what's your favorite TV show?
Oh yeah, because those questions have no correct answer.
Okay, so like yeah, like
cannot judge you based on my personal preference.
Like that's not going to factor in anyway.
Of course not. Of course not. The text run exam,
right.
Those questions are trivial. Okay, so of course, asking what's your favorite TV show? If it is not same as mine, you can lose point. No. That can become a joke. That could become a big joke.
Well, I was just asking because like when you go to put other grades like the midterm in, then it'll have an effect on it because it shows it as a 0
let me
out of
show
3.
it. Let me show this grade, something like this. You see, Daniel is asking the test run exam for 0. They're not counted towards your final grade. Okay. And to the midterm exam, this midterm exam is 15 points. Why 15 points? Because this part only contains the multiple choice, whose total point is 15. So you're going to be able to see some number out of 15 from here, from this column. And the next column is upload midterm exam here. This is about, obviously, the handwritten works. After grading those, I'm going to return the graded handwritten works to you. As to the number here, as to the grade here, for this particular column, I need to type in myself. And then so your total midterm 1 exam grade is this column number plus this column number. Does it make sense now?
Yep, thank you.
Sure. Of course, here, this column, the total is out of 15 points. Total is 15 points. This is out of 45 points. So total points is 60. Okay. So you sum them up, you over 60 is your grade. Okay, is your grade. As to the percentage here, no, they are not accurate. Okay, they're not 100% accurate. They are not 100% accurate. Because they're not taking into consideration of the weight. Okay, say homework just what, 10% or 5%? I can't remember. The midterm is 20%, right? The project is certain amount of percent. Not taking those into consideration. However, since you know every single grade you're receiving from this grade book, you will be able to calculate how much percent eventually you received yourself, right? And if you want to verify that, say by approaching to the end of the semester, you want to verify, say, Daniel is like, well, Dr. Zhou, my calculation ended with 95%. Therefore, well, of course, the final exam is not, the midterm 3 is not happening yet. I don't know how much I'm going to receive from there, but 95% for up to the date, is that about right based on your record? And then I go into my record to take a look, okay? And then reply, say, I'm sorry, Daniel, your calculations are wrong. You just have 75% or so on and so forth. And then we might have argue, but you know how to argue, right? Because you know all of the grid here. I just gave you an example showing how this works, right? Yeah, of course you would run 90%, then 95%, but we will see, okay? My point is you won't be able to miss any information, okay? You won't be able to. And when I tell you your grade, I have a very strong basis as well. I have a very strong record, very complete record showing why you are receiving that letter grade, okay? That has never been a problem in my classes. So don't worry. And another thing, this percentage in the gradebook's canvas is not accurate. Another factor is we might have a curving. The curved grade is not shown up here. The curved grade is not shown up here. Or I have to add one column here to show you the curved grade. However, that way gonna even mess up the percentage shown up here. So total here. So this total percentage from the gradebook, no, is not accurate. It's not very accurate. Any other questions you have? Any concerns? All right. Maybe I think the rest of the time, let's just briefly talk about the lab circuits. We studied two circuits in lab 5, and why we are seeing the waveforms we saw in the scope, right? Two circuits here, right? The first circuit is nothing but the last circuit in our last PPT slides, right? Everybody realize that? So what does it mean is during the first half cycle, let me write something here. To the first circuit, this is the source. This is source. This is VS. Okay, this is VS. This is VS. Then what does the output V naught look like? Right? What does it look like? It's very easy to first of all tell. You can roughly imagine. First half cycle here. These two would be on, right? These two no way to be on. Does it make sense? The first leg will be on. Second leg, no way to be on. Does it make sense? During this first half cycle. And during the negative half cycle, of course, the other way around. So second leg gonna be on. The first leg gonna be off for sure. Right? And therefore, during the first half cycle, what you have is the diode is on. If the diode is on and the zener is on as well. So the circuit is like what? So right, this is the circuit. Right. If it is on, then what is the model of it? Okay, this is the model of it. Does it make some sense? Be very careful of orientation here, okay? So you have a diode in this anode towards up, cathode towards down. And the corresponding, the AC large signal model is like this, right? Positive polarity at the top, negative polarity on the bottom. However, be very careful. The zener here, we are not using, the model of it is what? Because this is reverse bias array. Reverse the bias. And then this VZ is what? Is the breakdown voltage, not the forward cut-in voltage. That's why the polarity is what? It's opposite to that of the diode. Did I make myself clear here? The VZ is the breakdown voltage, which is designed to be small than normal, so that you can use the zener to protect the circuit and so on and so forth. So this VZ is not V gamma of the zener, okay? No, these two are not same thing. Breakdown voltage, remember, is the reverse biased voltage. That's why the model is like this. Of course, don't be panic. I'm not planning to have any zener in the exam, okay? Is that a relief?
Yeah.
I can't see your smiling face, so I have to guess. I think most of you guys are smiling now. There's no zener in the exam. I'm not planning to do that. But here I'm explaining why it's so. Does it make sense anyways? And if so, then you can imagine, then when it is on, once again, when this two is on, then what is the output voltage? or say the circuit. The circuit looks like what? Right? This is the output voltage. Right? The further V output equals what? Remember those three things? You need range. Okay, we roughly know the range. And then we know the circuits. And the third one is deriving the corresponding output voltage. Output voltage equals what?
V gamma plus BZ.
Here we go. There's a constant, right? Remember the cut, so-called cut in the output waveform. What is cutting? It's cutting a certain value, constant value. That's why you remember in the lab, what you guys did? When you apply a small magnitude of the V source, what happened? You're not seeing any cut. Why? Because it's not even reaching this guy. You're not even reaching the V gamma plus VZ, right? So what do? Increase the magnitude of the VS so that it's gonna exceed this V gamma plus VZ, and then you start to see the cutting, right? It's chop. Does it make sense? The more you increase your magnitude of the source, the more it's chopped off. Of course, however, essentially the chopping threshold remains same. It's just that like you increase your magnitude too much, so the chopped off part top here gonna be a lot as well, right? That's why you're seeing something like this, right? During the first half cycle. During the second half cycle is similar. It's the second lag functioning the same as the first lag during the first half cycle, right? So the result is going to be like this. And what is the chopping? What's the chopping here? Negative V gamma plus VZ, right? Same thing. That's why it looks like what trapezoidal, but it's not. It's just a chopped AC. It chopped the sinusoidal. Does it make sense?
Yep.
All right. Thank you. So this is why we are seeing what we saw in the lab. Okay. Obviously, there's a reason behind it. Okay. And the next circuit is the clamper circuit. The clamper circuit is not chopping. This capacitor clamper circuit is not chopping. It's not doing any chopping. It's just what? Clamp, or say shift your source. How to shift? This is a little bit tricky to understand. Even though the circuit is very easy, right? One diode, one capacitor, one AC source. However, it's not very easy to understand. So what's happening here is inside of this loop, you can easily have Vs equals to Vc plus V naught, right? This is very easy. KVL inside of this loop, right? This is very easy. And therefore, you can easily derive V naught just equals to Vs minus Vc, right? Vs is sinusoidal. This is given. This is given. What is Vc? This is not very easy, but can anyone imagine what is Vc at a steady state? By steady state, it means, I mean, you can imagine this circuit is what? Is charging, right? Look at the diode, allowing one-way current direction, blocking any possibility of the reversed current. Therefore, is what? It's trying to charge. It's actually charging the capacitor. Charging, of course, it takes time as transient. And then from certain amount of time on, the charging is done. Therefore, what is the Vc by then? What is the voltage across the capacitor? Can anyone remember? Not remember. Never taught this before. Can anyone imagine What is VC? This guy is equals to what? This is actually the real circuit. Okay, you can use this to charge your battery. Can AC charge battery? Of course it can. This is an AC charging battery. You don't have to apply DC. Can anyone imagine what is the VC, voltage across the capacitor eventually? Connor, any idea? Vs minus Vg. What is Vg then? V gamma. Nope, not quite. Not quite. Close. Connor, any idea? Connor is kind of offline, but how about, well, and Kevin saying Vs minus Vg. This is the result of the, I think maybe the circuit analysis. However, be very careful. The Vs is a sinusoidal. If you're saying Vs sinusoidal minus a constant, the result is still time varying sinusoidal. Does it make sense, Kevin? That couldn't be the steady state then. Does it make sense? So it's not Vs minus Vg, because Vs minus Vg is still not steady state yet. Right? So keep thinking, it's still charging. When is it going to stop charging? In other words, just reach the steady state. The voltage is stabilized by the capacitor. The voltage across it doesn't change anymore. That's the steady state. Once again, you're thinking of the battery, right? When it's done, is the voltage stabilized at the full voltage, fully charged, right? So what is the voltage of the capacitor? Any experience? Have you ever guys used the diode and the AC source to charge your battery? Probably not. It works. Okay, it works. If any answers, please speak out. Once again, speak out. All right, if no more answer, the answer is this. Okay, when steady state reached, VC is equals to, let me use the red color, is equals to the peak voltage of the source Vs, which is constant. Does it make some sense? You can imagine that your AC is time varying, right? The source is time varying here. Well, but you're charging a battery, you charge until the voltage across it is stabilized, right? Stabilized. When is going to stabilize? If at any moment your source voltage is still higher than the capacitor voltage, it's going to keep charging, right? That's not steady state. So it only reaches the steady state when the source, no matter how you time vary, how you sinusoidal values to vary, you are not be able to exceed the peak value of the capacitor, which is the peak value of himself. Does it make sense? Because as long as your source can still exceed the capacitor voltage. It's gonna keep charging, right? Until one moment the capacitor voltage is already at the peak of the source, then your source has no way to exceed this value anymore, right? And then stop charging. Does it make some sense? Is it even close?
Yeah, I think it makes sense now that you explain it.
Yep. Because if good. So if the capacitor voltage is not peak, the VS still got a chance at certain amount of time or certain moment still exceed that voltage. Then you're gonna keep charging. You're gonna absolutely keep charging. Well, Kevin, so long. I'm too tired to read this. Can you speak it?
To charge like a 12-volt DC battery with wall voltage, we just would have to add resistors between the VS and the capacitor to bring the voltage peak down. Then
you're adding resistor. That's good, but resistors function is to limit the current. You need a diode.
I don't think I understand. So, like, if we use figure 2, the clamper circuit, and between the VS and the capacitor, we add resistors to bring us down to the voltage peak that the capacitor sees at 12 volts. That's how we would charge a 12-volt battery, or would we need more diodes in there?
You're using what is your AC source?
The wall in my house.
The wallet? No. You can't do that. You can't do that. You need to reduce the AC peak value to be same as the battery voltage.
So would I just use resistors to do that?
Use the resistor. You can only limit the current. Because eventually you can imagine after charging your battery is there and no current, because if there's still current, it's still charging or discharging. Does it make sense? There won't be any current. No current, then your voltage through your resistor is zero. It won't help to drop down the voltage. Does it make sense? All right, so we keep going. Well, I'm not receiving. Kevin's saying his audio keeps cutting out on his side. Well, I think so. His connection is sometimes is bad. But anyways. Does what I said make sense to the rest of you guys? Kevin suggests to put the resistor in series. However, when charging is done, then it's not going to help dropping the voltage from the source, okay? Because no current. And you need to have a proper AC source with proper peak value of it, okay, to charge the proper battery. That way it's gonna work. And but if this is okay, then how to plot your AC source VS is over here. This guy is the peak value, right? So what happened? Your peak value is gonna become 0, isn't it? So your entire waveform gonna shift down. Like this. Entire AC sinusoidal waveform gonna shift down by how much? Peak value of the AC source. Okay. This is what we see in the lab. This is what we see in the lab. This is what we see in the lab. And afterwards, we are adding the resistor parallel with the diode. Can anyone understand what that's resistor for? Anyone can understand what that resistor parallel is for?
Don't the resistors shift it up to the original?
Why is that? In other words, what is resistor is for in this functioning circuit? It's actually like this. Okay? It's actually like this. How you understand this circuit is like this. Like I said, the original circuit is like this, right? Yeah, this is the original circuit. The current can only flow this way, this one way. So the voltage is built up across the capacitor. Okay? So there's nothing but charging. However, if one day you give a parallel resistor, what's the difference is in nature is this. Back to here once again. So you understand that it charging and charging. There's no way to discharge. Does it make sense? In this circuit, no way to discharge because the discharge requires the current flow backwards. Due to the diode here, you cannot do that. It doesn't work that way. However, if you have a resistor parallel with diode, okay, guess what? It's providing a discharging path. It's providing a discharging path. Does it make sense? So this way charging, this way discharging. And well, maybe I think we can stop here. And once again, the exam is all right. Okay, exam won't involve the zener, won't involve the clamper either. So you don't need to be panicked. However, this circuit analysis, when you involve a diode, it becomes not quite easy. Anyone knows the circuit with diode and the circuit without diode? What's the difference in nature? The circuit with diodes or even future transistor is what?
Are you asking about the clamper circuit without a diode?
No, not is a generic question. It's not for any specific circuit. So circuit involving the diode, involving the switch, involving, because diode is nothing but a switch you can imagine, on or off, right? Or diode involving the amplifier, not amplifier, the transistor. Why they're so hard to analyze? This is so-called, I think you guys ever heard of it. These circuits are typical what? Nonlinear circuit. Okay? They're typical nonlinear circuit. Whatever we learned from 235, those are, no matter how complicated you feel or your complaint, they are still linear circuits. Okay? The easiest case you could have. Once you involve the diode, transistors, and especially in the future power electronics, okay, everything is nonlinear. Nonlinear. That's why it's not easy. Everything becomes not easy. Okay, it's not linear. All right, so I think I'm done with what I want to talk today. So the rest of the time for you guys to ask questions. Anything I can do for you to make your upcoming midterm 1 easier?
Are there any
yeah.
Are there any specific problems out of the book that you would recommend trying out?
Out of the book. The basic idea is the ones very close to our in-class example. Those are so-called good examples. Let me see the this is our homework 2. Homework 2, problem 14 and 37, they're pretty much the things we have learned from the lecture. And these two diode circuits, they're fine. And this is about Zener. No, not quite relevant to our exam. This is also something we have talked about too, so. Homework 1, what do we have? Here I want to bring up one thing. Okay, look at the homework 1.44. This problem. If you're looking at the solution here, the solution is directly using the diode model to calculate. This is obviously a DC circuit, since only DC supply on top. But in the exam, remember, we have learned this from the lecture. The proper procedure is you begin with assuming the diode is on, and then you have good reason, a reasonable reason to apply that diode model, which is the DC supply. Without this assumption, it doesn't make sense for you to start with the DC supply model. Okay, and after this assumption, you apply this model, and then you go ahead to find ID, the current, to justify your assumption. Okay. These are very important 2 steps. Assume at the beginning, and then justify your assumption in the middle. If it turns out that, okay, your assumption was right, then it's good. If it's not right, you need to do something else. Remember, I provided a flow chart, right? It's a kind of flow chart for you to follow. It's a very logical procedure over there. Can anyone remember?
If you do the analysis with the circuit on and the current across the diode is negative, then you assume it's off and you open the circuit or the diode.
Correct. That's the logic I'm looking for in your answer. How about the rest of you guys? Do you remember this logic procedure? Follow this procedure. Okay, at the beginning, you're applying the diode on model DC supply. No sense. Essentially, no sense. If you're lucky, you might be right. If you're not, you definitely are wrong. And without justification, even you're right. Without justification, you're still gonna lose some point. Is that clear what I'm talking about? Any questions? as long as you have the notes, you should be able to understand what I'm talking about. They're big, because in the notes, there's a flow chart, okay? A step-by-step procedure there. Okay. Such a kind of answer, no, I don't like. I really don't like. I don't like. Without assuming it is on, you're applying directly to V gamma. Why? Why is that? Because if it is off, the circuit is not even safe. Okay, that makes no sense. So out of textbook, well, the textbook problem, of course, if you think it's close to the in-class example, you can try it out. And if you have any questions, feel free to ask. We can discuss. And if ask me to bring up some good examples out of textbook, homework problems are fine, even though some of the solutions I don't like. Any other information? Any other questions?
A question regarding the equation sheet.
Say that again?
Just a question regarding the equation sheet. Is it you said one side, right? Not two. Just one side.
What do you mean by one?
One side of equations, not two sides of equations for the.
Two sides. Double sides.
Okay, thank you.
To be honest, I'm not seeing any difference from my end, but because we don't have much formula to write down. But if you feel more comfortable, feel free to have two sides. That's okay.
Okay, thank you.
Yep. My class is not for memorizing. It's not like a history problem. The more cheat sheet you have, the easier time you're gonna have during the exam. No, not necessarily. Really not. It's about how much you understand, how much logic you're able to hold. Okay. It's kind of assessing your capability rather than your memory. Cheat sheet, okay, the two sides. Okay, that two sides, that's fine. Any other questions?
Is homework 1 graded yet? I didn't see anything on it.
Homework 1 graded yet? Let me see. Oh, probably not yet. Let me see. No, not yet. Not yet. I'm very close to finishing the grading of homework 1, but something else interrupted me. So I stopped, and afterwards I forgot, I think. But I will try to make that happen as soon as possible. How about that?
Okay, thank you.
Sure. Any other questions? Anything else I can provide? Anything? Well, multiple choice problem, no matter how many of them, okay, and there's one thing I'm gonna keep very very tight, is the questions are definitely something we have ever discussed in the lecture, okay? Since we have recorded lectures, so you guys will be able to review some, okay, from the recorded lectures. It won't be something you never heard of, okay, except you forget or you missed. Otherwise, it's definitely something we have ever discussed. I have ever taught in a lecture. That's for sure. Okay, that will be for sure. Not something you never heard of. Well, anything else I can do for you? Nothing? All right, we can end it here, and good luck with the midterm 1. Okay? Right, thank you. Bye.